So sometimes the median of a density curve is referred to as the equal areas point. Okay? And we saw that yesterday. We talked about two distributions yesterday. One distribution we talked about was the normal distribution. And we said in the normal distribution, the median was right here in the middle. And it was the special value of x, which we called mu, it was also the mean, such that the area below that value is 50% of the total area, and the area above that is 50% of the total area. In the case of a density curve, we said the total area in the density curve is 1, so this area on the left is 0.5, the area on the right is 0.5. We saw another distribution yesterday, right? We saw the uniform distribution. Okay? And a uniform distribution had the property that it was the same height everywhere, and it ended at a particular number. Let's pretend it ended at the number n. If it ended at the number n, first question I want to ask you is, how tall is this curve? You actually know. Okay. It'd have to be 1 over n tall. Now the question is, why is that the case? Well, we know two rules about density curves. One, they always have to be above the horizontal axis, which the curve I've drawn here, this uniform distribution and the standard normal distribution also, both have that property. They never go below the x-axis. Secondly, the total area under the curve has to be 1, right? So if this is a rectangle and it has a length of n, then the height, or whatever you want to call it, has to be 1 over n, because n times 1 over n equals 1. So that has to be true. Okay, where's the median? Is there a median here? Yes, right here at 1/2 of n. That's the point where you'd have exactly half the area below, or an area of 0.5 below that point, and an area of 0.5 above it. So the median of a density curve is considered the equal areas point. Okay, now that we've said that, what about the mean of a density curve? Well, the mean of a density curve is called the balance point of the distribution. So what I want to do next is we're going to look at a curve, a density curve that I'm going to make up, and we're going to show that where the mean is and where the median is by using these two new ideas. The idea that the mean is the balance point and that the median is the equal areas point. Sorry. Let's go right back to the normal distribution. Here it is. Okay? We know the median already. It's right in the center. There's the median, because that's the equal areas point. So, I want you to imagine that this normal distribution is going to be placed on top of like a triangular base. Here's what I mean. Suppose I put a triangle here like this. Here's the table, or some kind of flat surface, and I'm going to take this normal distribution, this blue thing, and put it down on top of that triangle. Do you think it would balance in the position I've placed it right now? No. What would happen is the side on the right, this stuff over here, would swing down. Okay? Because we haven't balanced it. As a matter of fact, I think you know, where should we place this thing so that it balances? Right in the middle. So it would be nicer if we put the triangle here. So that black triangle is the perfect position so that it would balance. Now, we're not surprised by that, because this distribution is symmetric. And we already discussed in a symmetric distribution that the median equals the mean. We expect that to happen. That's mu. Okay? So this is not surprising. But what about in a non-symmetric distribution? non-symmetric distribution. That's what I want to discuss next. So I'm going to draw an interesting curve for us. Ready? Here we go. Looks like this. Suppose this is our density curve. I want you to think of it. It's made up of a rectangle that looks like that. Okay, and then another rectangle like that. Okay? So I just want you to imagine for a second there's a dotted line here. Okay? And what I'd like you to know is that the area of this one, this area, equals 0.5. And so is this area. This area equals 0.5. Okay? So, having said that, where is the median located? Yeah, that's right. We know that because the median is the equal areas point. So there's the median, and we have equal area on both sides. This area is 0.5, that area is 0.5. Now, the question is, what would happen if we put that triangular base where the median is? So I'm going to just take this picture for a second. I'm going to take it away for a minute, and we're going to imagine that. Go to a new page. So let's pretend where this median was, I decided to put that triangular base I described in the other problem. So let's say I put the triangular base right there. Here's the horizontal surface. Do you think that this density curve would balance on that point? Okay. The answer is no, because this rectangle, and like for example, this rectangle here, this blue rectangle, and this red rectangle, they're the same area. So you could think of them as having like the same weight. But the rectangle, the red rectangle on the right, is further away from the center created by this red triangle. So I'm claiming that this thing will tip down on the right. Okay? So this point here, this dotted line where the median is, cannot also be the mean. So my question to you is, which way do you think I should move the triangular base so that I balance this? Yeah, and the answer is very good. You're going to want to take the triangular base and move it slightly to the right. So if we did that, what I'm saying is that the mean has to be somewhere to the right of the median. Now, I'm not exactly sure where it should be, but let's just say that that's where the mean is. Okay? All right. And I claim that makes total sense based on what we said before. We said that in a distribution that's slightly skewed right, that the mean should be greater than the median. Okay? And this just confirms that. So what I'd like you to do is more density curves. Okay? So I want you to consider a density curve that looks like this. It's a right triangle. Goes through the point 0, 0. And it goes through some point out here. I don't know what it's called. I'm going to call it x comma 0. And then what's also special is its height is the same as its width. So up here is the point x comma x. Okay? So what I'd like you to try and do is, let's try and answer a couple of questions. First off, I want you to find out what x should be. So find x. And then once you find x, then I'd like you to answer some questions like, what's the probability that x is less than 1? And then, well, we'll try that. And then one more question, problem 3. Sorry? This says p. Let me erase that. That's 0, 0. Sorry. So again, I wanted the probability that x is less than 1. I also want to know the probability that x is less than or equal to 1. And then 4, the probability that x is greater than 1. So those are the things I'd like you to try. All right, so let's discuss this problem. We we know that a density curve has to have a total area of 1, and we know that this is a triangle. So the base, we just know that the length is really x, what we called it, and the height is also x. So we can write this formula, 1/2 of x times x, because it's really just 1/2 base times height, and that has to equal 1. So this is just some algebra. 1/2 x squared equals 1. That means x squared has to be 2. So x is the square root of 2. So now you know some coordinates. This is square root 2, 0. This is square root of 2, square root of 2. Okay. So we found x. It's rad 2. Let's talk about the probability that x is less than 1. So yesterday we discussed that if you want to find probabilities using density curves, it really just turns into an area problem. Do you remember that yesterday? So if you want the probability that x is less than 1, all you do is you find 1 on the x-axis, we draw a dotted line up, and we want the area that's less than 1. That's all you have to do. Okay, well that area is just 1/2 of 1 times 1. You might say for a second, how do I know it's 1 times 1? Well, the base is definitely 1. And we know that this line here, this side of the triangle, this hypotenuse, it goes from 0, 0 to rad 2, comma, rad 2. Well, that means when it goes through x equals 1, y has to be 1. So they're the same. The x and y coordinates are the same here. So the answer to that probability is just 1/2. Okay, that's sort of interesting. What do we know about x equals 1 then? It has a very special meaning in this distribution. Correct. This is actually the median. And we know that because the area to the left of 1 is 1/2, and that means the area above it is 1/2. Now, this is sort of a trick question, this question number 3. If we give it some thought, it's just like question 2, except I also want to include the area that goes with 1. Right? So that means that above 1, we should take this dotted line and make it solid. The question you should ask yourself is, does that add any area to this triangle? No, it does not. I see people shaking their heads saying no. So this is also 1/2. Okay? And question 4, you have an option. You can do that the easy way or the hard way. Okay? So here's what I'm hoping you'll do. You'll look at it and say probability x is greater than 1 is really saying the opposite of the question 3. So you can write this the following way. You can say, hey, that's 1 minus the probability x is less than or equal to 1. And that's because these things are opposite events. X being greater than 1 is the exact opposite of x being less than or equal to 1. So this is just simply 1 minus 1/2, which is 1/2.